Hello there, and welcome to this sleepy universe zone. The real reason no one can survive deep space is not because it is cold, not because it is far, and not even because it is empty. It is because the moment you enter it unprotected, your body begins to fail in ways that are immediate, silent, and completely irreversible before you even understand what is happening. There's no dramatic countdown, no slow fading into darkness. Within seconds, the systems that keep you alive begin collapsing all at once. And the most unsettling part is this: you would still be conscious just long enough to realize that something is very wrong, but not long enough to do anything about it. That is the truth most people never hear. And once you understand it, the idea of floating peacefully in space will never feel the same again. Right now, as you sit here breathing, your body is operating inside a narrow band of conditions so stable and so perfectly balanced that you almost never notice it. The air around you presses gently against your skin. Oxygen flows quietly into your lungs. Your blood carries it to billions of cells without effort. Every heartbeat, every breath, every signal in your brain depends on this invisible balance. You do not have to think about it. Earth does it for you automatically, constantly, reliably. But what if all of that disappeared at once? What if the very environment your body depends on simply stopped existing? This is not a distant, abstract idea. This is exactly what deep space is. Not just a place without air, but a place that actively removes every condition your biology assumes will always be there. No pressure, no breathable oxygen, no thermal stability, no protection from radiation. It does not just challenge survival, it erases the possibility of it. And this is where this story becomes personal, because this is not about astronauts in movies. This is about you, your lungs, your blood, your brain, your cells. If you were placed into deep space without protection, the laws of physics would begin acting on your body immediately, not out of malice, not out of intent, but simply because that is what the universe does. It follows rules, and those rules were never designed for human life to exist out there. So why should you keep listening? Because tonight, we are not just going to say that space is dangerous. We are going to walk through exactly what happens to the human body, step by step, second by second, when it is exposed to deep space. We are going to break apart the myths you have seen in films and replace them with something far more fascinating and far more unsettling. You will understand why pressure matters more than you think, why oxygen is only part of the story, and why the true danger of space begins before you even lose consciousness. And as you listen, something subtle will begin to shift. The way you think about the night sky, the way you understand your own body, the way you feel about this thin layer of air surrounding you right now. If you find this kind of exploration calming or strangely grounding, you can gently support this space by leaving a like, not as an obligation, but as a quiet signal so that this kind of content can reach others who might need the same sense of perspective tonight. Now let us begin with the first thing space takes away from you. If there's something so fundamental that you have never had to question it, even once in your life, pressure. You might think the most dangerous moment in space is when you stop breathing, but the truth is far more unsettling. Because long before oxygen becomes the problem, your body is already breaking apart under a force you have never once had to think about in your entire life. Pressure, and the instant it disappears, everything inside you begins reacting in ways that feel almost impossible to imagine. Right now, as you sit here, your body is perfectly balanced against the weight of the atmosphere, about 101,000 pascals pressing gently from all directions. And that pressure is not just surrounding you, it is part of you. Your lungs expand and contract because of it. Your blood carries gases because of it. Your cells maintain their structure because of it. It is the invisible foundation of every system keeping you alive. But the moment you enter a vacuum, the foundation is removed instantly, not gradually, not gently, but all at once. And the result is not dramatic in the way movies show. It is far more precise and far more ruthless, because the gases dissolved throughout your body no longer have pressure holding them in place. And like opening a bottle of soda, they begin to come out of solution, forming bubbles everywhere at once. This is called ebulism. And unlike anything you have experienced before, it is not localized, it is systemic. It happens in your blood, in your tissues, in the fluid around your eyes, and even within microscopic spaces between cells. Your circulation begins to fail, not because your heart stops, but because the blood it is trying to pump is no longer behaving like a liquid. It is becoming a mixture of fluid and gas, disrupting flow, blocking vessels, starving tissues of oxygen even before your lungs have fully emptied. And at the same time, your body begins to swell, not explosively but noticeably, as gases expand beneath your skin, stretching it outward in a way that feels tight and unnatural. Your body can actually expand to nearly twice its normal volume without immediately tearing because skin is surprisingly elastic. But that expansion is a sign that internal equilibrium has been completely lost. And then something even stranger begins to happen. The water inside your body starts to change state, not because of heat, but because of pressure. Boiling is not just about temperature. It is about the balance between liquid and vapor. And when external pressure drops low enough, water can boil at temperatures far below what you would expect. In the near vacuum of space, the boiling point of water falls to around normal body temperature, which means the moisture on your tongue, the thin layer covering your eyes, and the fluids lining your lungs begin to vaporize almost instantly. This is not violent like boiling water on a stove. It is a rapid, silent transition where liquid turns into vapor and disperses into the surrounding vacuum. And for a brief moment, if you were conscious, you might feel a strange cooling sensation as this evaporation pulls heat away from your tissues. But that sensation would be fleeting because the damage is already spreading through your body. Now consider your lungs, the very organs you rely on for survival. In this environment, they become extremely vulnerable because if you instinctively hold your breath as pressure drops, the air inside expands rapidly and can rupture delicate lung tissue within seconds, forcing gas into your bloodstream and chest cavity, compounding the damage already being caused by ebulism. This is why trained astronauts are taught never to hold their breath during rapid decompression. But even if you react perfectly, even if you exhale immediately, it only delays one specific type of injury. It does nothing to stop the larger process unfolding throughout your body, because the problem is no longer about breathing. It is about the fundamental physics governing liquids and gases under pressure, and those laws do not pause or adjust for human survival. They continue acting on your body without interruption. Within seconds, your circulation is compromised, your tissues are swelling, and the delicate chemical balances inside your cells are being pushed beyond their limits. And yet, in this brief window, you are still conscious, still aware enough to feel that something is deeply wrong but unable to understand or control it. This is the moment where reality diverges completely from fiction. There is no slow, graceful drifting, no time for final words, just a rapid internal unraveling driven by the absence of something you have never had to notice: pressure. And as this process continues, another critical system is already beginning to fail, one that will determine how long your mind can remain aware before everything fades. Because even if pressure alone did not end you, the next thing space takes away will. By the time your body begins to swell and your blood starts to foam, something even more critical is already slipping away. And unlike pressure, this is something you instinctively understand: oxygen. But what makes this stage so unsettling is how quickly it happens and how little control you have over it. Because in deep space, you're not simply deprived of air, you are cut off from the entire process that allows oxygen to enter your body in the first place. Your lungs are no longer exchanging gases. There is no reservoir of breathable air, no pressure gradient to draw oxygen inward. And whatever oxygen remains in your bloodstream is all you have left. A finite supply already being consumed every second by your brain and vital organs. And here is where perception begins to distort reality. Because for a brief moment, you might still feel conscious, still aware, perhaps even thinking clearly. But this clarity is deceptive. It is the final phase before the rapid decline begins, because your brain is an energy-intensive organ, consuming about 20% of your body's oxygen, despite making up only about 2% of its mass. It cannot store oxygen. It depends on a continuous supply, and the moment that supply stops, the countdown begins. Within seconds, oxygen levels in your blood start to fall. Neurons begin struggling to maintain electrical activity. Signals become weaker, less coordinated, and then something subtle but profound begins to happen. Your awareness starts narrowing, not in a dramatic blackout, but in a gradual dimming. Vision may tunnel. Sounds may seem distant. Thoughts may feel slower, harder to hold on to. And this is not because your brain is shutting down all at once. It's because different regions are failing at slightly different times. Higher cognitive functions are often the first to go. Reasoning, decision-making, self-awareness, leaving behind a fading sense of confusion. And then, within about 10 to 15 seconds, the oxygen level drops below the threshold needed to sustain consciousness, and you lose awareness completely. No pain, no dramatic realization, just a quiet, abrupt absence of thought. This is one of the most misunderstood aspects of space exposure, because many imagine a prolonged struggle for breath. But in reality, the process is far faster and far less perceptible than that. You do not suffocate in the way you would underwater or in a sealed room. You simply run out of usable oxygen and your brain shuts down. And while this might sound almost merciful, it is important to understand that even after consciousness is lost, the processes inside your body do not stop. Your heart may continue beating for a short time. Your cells continue consuming what little oxygen remains, but without replenishment, irreversible damage begins quickly. Brain cells are highly sensitive to oxygen deprivation. Within minutes, they begin to die, and although in controlled environments, rapid reoxygenation can sometimes reverse early damage. In the vacuum of space, there's no such intervention, no rescue, no restoration, just the continuation of a process that was set in motion the moment pressure disappeared. And this is where another layer of reality becomes clear. Because while oxygen loss is what ends consciousness, it is not the only thing happening. It is just one part of a larger cascade of failures, all occurring simultaneously. Your circulation is already compromised by gas bubbles. Your tissues are already swelling. Your body temperature is beginning to shift. And beyond all of that, there is another invisible force acting on you. Something that does not need seconds or minutes to begin its work: radiation. And although it may not be the immediate cause of death in these first moments, it is always present, always interacting with your body at a level you cannot see or feel, quietly altering molecules, damaging cells in ways that would become devastating over time. And as we continue, you will begin to see that deep space is not defined by a single lethal factor, but by the way multiple forces combine, each one stripping away a different layer of protection until nothing remains. And by the time oxygen fades, your body is already far beyond the point where survival is possible, because the environment itself has removed every condition that life depends on. Most people imagine that if you were exposed to deep space, the first thing you would feel is freezing cold, an instant transformation into ice, a body locked in stillness within seconds. But this is one of the most persistent misconceptions about space, and the reality is far more complex and far more counterintuitive, because temperature in space does not behave the way it does on Earth. And understanding this requires letting go of the idea that cold is something that simply surrounds you, because in a vacuum, there is almost nothing there to transfer heat. No air molecules to carry warmth away from your skin, no medium to rapidly absorb energy from your body, which means that despite the extreme cold of space, you would not freeze instantly. In fact, the loss of heat from your body would occur relatively slowly compared to the rapid internal failures already taking place. And this creates a strange contradiction, because while space is often described as being near absolute zero, around minus 270 degrees Celsius, that temperature refers to the background radiation of the universe, not to a substance actively drawing heat away from you. On Earth, heat transfer happens through conduction when you touch something cold, convection when air or water carries heat away, and radiation when energy is emitted as infrared waves. But in space, only radiation remains, and radiation is a much slower process for something at body temperature. Your body continuously emits infrared radiation, losing heat gradually over time. But this process takes hours, not seconds, which means that in the brief window before unconsciousness and death from other causes, temperature is not the primary threat. And yet, there is another side to this that is often overlooked, because while space does not remove heat quickly, it also does not protect you from incoming energy, particularly from a nearby star like the Sun. Without an atmosphere to filter or scatter radiation, solar energy reaches you directly. And if part of your body is exposed to sunlight, it begins absorbing that energy, while the side facing away radiates heat into space, creating an extreme temperature gradient across your body. One side warming potentially to temperatures above the boiling point of water, while the other side cools toward freezing. And this uneven distribution of heat is something your body is not designed to handle. On Earth, temperature differences are moderated by air circulation, by conduction through materials, by the simple presence of an environment that redistributes energy. But in space, there is no such balance. Heat is either absorbed or lost, with no intermediate process to smooth it out. And while you would not be conscious long enough to experience this in a meaningful way, it highlights a deeper truth about space, that it is not simply cold or hot, but fundamentally unregulated, an environment where energy flows according to physical laws without regard for biological stability. And this becomes even more significant when we consider long-term exposure, because for astronauts inside spacecraft or suits, temperature control is one of the most critical engineering challenges. Systems must constantly manage heat, removing excess energy generated by the body and electronics while protecting against external radiation. Failure in these systems can lead to overheating or hypothermia even within a controlled environment. And this reinforces the idea that survival in space is not about enduring a single condition, but about maintaining a delicate balance across multiple variables simultaneously. Pressure, oxygen, temperature, radiation, all interacting in ways that require constant regulation. And without that regulation, without the protective systems that recreate Earth-like conditions, the human body does not simply struggle. It fails rapidly and completely. And as we move forward, it becomes clear that even if pressure and oxygen could somehow be managed, even if temperature could be stabilized, there is still another force acting continuously, invisibly, and relentlessly, one that penetrates deeply into matter itself. And unlike the others, it does not need time to begin its work, because it is already there, filling the vacuum of space with energy that never stops moving, radiation. Even if you could somehow solve the problems of pressure, oxygen, and temperature, even if you were perfectly stabilized inside an environment that mimics Earth, there is still something in deep space that never truly goes away, something you cannot see, cannot feel in the moment, and cannot escape without massive protection, radiation. And unlike the immediate effects we've explored so far, radiation does not rely on seconds to begin its work. It starts the instant you are exposed, interacting with your body at the level of atoms and molecules, quietly altering the very structure of your cells, because space is not empty in the way we imagine. It is filled with high-energy particles and electromagnetic radiation, traveling across vast distances, originating from the sun, from distant stars, from supernova explosions, from regions of the universe so energetic that they accelerate particles to speeds approaching the speed of light. And when these particles encounter your body, they do not simply pass through harmlessly, they collide with atoms, ionizing them, knocking electrons out of place, breaking chemical bonds, and damaging DNA in ways that your body may not be able to repair. On Earth, you are protected from most of this by two powerful shields, the atmosphere and the magnetic field. The atmosphere absorbs a large portion of incoming radiation, while the magnetic field deflects charged particles, guiding them away from the surface. And what does reach you is only a fraction of what exists in space. But beyond that protection in deep space, the full intensity of this radiation environment is present, and it is constant. There is no pause, no safe zone, just a continuous flow of energy passing through everything in its path. And this includes you. Now, in the context of immediate exposure, radiation is not what causes you to lose consciousness within seconds, but it is still acting on your body at the same time as every other process. Each particle that strikes you leaves behind a trail of damage, a microscopic path where molecules have been altered or destroyed. And while a single event might not seem significant, the cumulative effect over time becomes profound. This is why astronauts who spend extended periods in space receive significantly higher doses of radiation than people on Earth. Even in low Earth orbit, where some protection from the magnetic field still exists, their exposure is dozens to hundreds of times greater than normal. And over months, this increases their risk of cancer and other health issues. But in deep space, the situation is far more extreme, because one of the most dangerous forms of radiation comes from galactic cosmic rays. These are not simple photons like visible light or even ultraviolet radiation. They are atomic nuclei, stripped of electrons and accelerated to enormous energies, traveling through the galaxy for millions of years before encountering anything. And when one of these particles strikes human tissue, it does not simply interact with a single cell. It creates a cascade of secondary particles, a chain reaction that spreads damage across multiple cells, disrupting biological structures in ways that are difficult to repair. And what makes this particularly challenging is that these particles are so energetic that they can penetrate significant amounts of material, meaning that even shielding is only partially effective. And this is one of the reasons why long-duration space travel is such a complex problem. Because while you can design systems to manage pressure and oxygen and temperature, radiation is far more difficult to block completely, as it requires mass, dense materials that can absorb or deflect energy. But adding that mass makes spacecraft heavier, more difficult to launch, more expensive to operate, creating a constant trade-off between protection and practicality. And for an unprotected human in deep space, there is essentially no defense at all. Every particle that passes through becomes part of an ongoing process of damage. And while you would not live long enough in a vacuum to experience the long-term consequences, this radiation environment defines the broader challenge of surviving beyond Earth. It is not just about immediate threats, but about the accumulation of invisible harm over time. And this leads to a deeper realization that deep space is not a single hazard, but a layered environment where multiple forces act simultaneously, and each one capable of causing harm in its own way. And even if one could be mitigated, the others remain, constantly shaping the limits of what is possible for human life. And as we continue this exploration, the focus begins to shift from what happens in the first seconds of exposure to what would happen if, somehow, those first moments were survived, because understanding that scenario reveals even more about why deep space remains fundamentally incompatible with life as we know it. If we take everything we have explored so far and compress it into a single timeline, what emerges is not a slow progression, but a rapid cascade of events, each one overlapping with the next, each one reinforcing the others, creating a sequence that unfolds in less than a minute. And understanding this timeline brings clarity to the central question of why survival in deep space is impossible, because it shows how quickly the body moves from stability to complete failure. At the moment of exposure, the pressure drops instantly from 1 atmosphere to near zero. Within the first second, gases in the lungs begin to expand. If breath is held, lung tissue may rupture. If exhaling air rushes out rapidly, at the same time, moisture on the tongue and eyes begins to vaporize as the boiling point of water drops. Within 2 to 3 seconds, ebullition begins in earnest. Dissolved gases form bubbles throughout the bloodstream and tissues. Circulation becomes increasingly disrupted. By 5 seconds, swelling becomes noticeable as gases expand beneath the skin. The body begins to lose its normal shape slightly. Within 8 to 10 seconds, oxygen levels in the brain drop below the threshold needed to maintain consciousness. Vision narrows, awareness fades, and then consciousness is lost. At this point, the person is no longer aware of what is happening, but internally the processes continue. The heart may still be beating, but it is pumping blood that is no longer functioning properly. By 30 seconds, the combination of oxygen deprivation and circulatory disruption begins causing irreversible damage to the brain and other organs. By 60 seconds, severe neurological damage is likely. Even if repressurization were possible, recovery would be uncertain. Beyond 90 seconds, cardiac function begins to fail. The systems that sustain life are no longer operating in any coordinated way, and within a few minutes, clinical death occurs. No brain activity, no effective circulation, no possibility of revival. And what makes this timeline so striking is not just how fast it unfolds, but how little of it is experienced consciously. The window of awareness is measured in seconds. After that, the body continues through the sequence without perception, driven entirely by physical processes. And this is supported by real-world incidents, where individuals have been exposed to near vacuum conditions for brief periods in controlled environments, such as vacuum chamber accidents. Some have reported the sensation of saliva boiling on their tongue, followed by rapid loss of consciousness. And when repressurized, within a short time they recovered. But these cases are limited to exposures of around 10 to 15 seconds. Beyond that, the damage becomes increasingly severe and survival becomes unlikely. And this reinforces a critical point, that while the human body can tolerate extremely short interruptions in normal conditions, it cannot withstand the complete removal of those conditions for more than a brief moment. And this is why deep space is fundamentally different from other extreme environments on Earth. It is not simply harsh or challenging. It is immediately incompatible with the processes that sustain life. And even with advanced technology, the goal is not to adapt the human body to space, but to recreate Earth-like conditions around it, to build systems that replace what space removes. Because without those systems, survival is measured not in hours or minutes, but in seconds. And as we continue forward, this understanding begins to shift from the immediate experience of exposure to the broader question of what it takes to prevent this sequence from ever starting. Because the only way humans survive in space at all is by carrying an artificial version of Earth with them. And that introduces a new set of challenges that are just as complex and just as unforgiving as the environment itself. If deep space removes every condition your body depends on, then the only way to exist within it is not to adapt to space, but to replace it. And this is where one of the most misunderstood ideas begins to shift. Because a spacesuit is not simply a protective layer, it is a complete life support system, a fragile artificial environment that must replicate just enough of Earth to keep you alive. And the moment you understand that, you begin to see how narrow the margin for survival really is, because every function your body performs without effort on Earth must now be actively maintained by engineering. Pressure must be generated and held constant. Oxygen must be supplied at the correct partial pressure. Carbon dioxide must be removed before it becomes toxic. Temperature must be regulated continuously. And all of this has to happen inside a sealed system that you are completely dependent on. And if any one of these systems fails, even briefly, the same cascade of events we have already described begins again. Not because something went wrong with your body, but because the environment around it is no longer stable. Now, consider pressure. A typical modern spacesuit operates at around 4.3 pounds per square inch, significantly lower than Earth's atmospheric pressure, but high enough to prevent embolism and maintain basic physiological function. However, to compensate for this lower pressure, the suit uses nearly pure oxygen, ensuring that the partial pressure of oxygen remains sufficient for breathing. And this introduces its own risks, because pure oxygen environments are highly flammable. Materials that would not normally burn can ignite easily. And this is not theoretical. It has been demonstrated in tragic accidents where high oxygen environments led to rapid, uncontrolled fires. And so even in solving one problem, another is created, and this pattern repeats across every system in the suite. Oxygen supply must be carefully controlled. Too little, and hypoxia occurs. Too much, and pressure or toxicity becomes an issue. Carbon dioxide removal relies on chemical scrubbers such as lithium hydroxide, which react with CO2 and remove it from the air. But these systems have limits. Once saturated, they stop working, and if not replaced or regenerated, CO2 levels begin to rise, leading to confusion, dizziness, and eventually unconsciousness. Temperature control presents another challenge, because in the vacuum of space, heat cannot be carried away through air. So suits use liquid cooling garments, networks of tubes that circulate water around the body, absorbing heat and transferring it to radiators, where it can be emitted as infrared radiation. And if this system fails, the astronaut does not freeze. They overheat because the body continues generating heat with no efficient way to remove it. And then there is mobility, something that seems simple until you consider that a pressurized suit naturally resists movement. Every joint must be engineered to allow bending while maintaining a seal. Every motion requires effort against internal pressure. Even closing your hand becomes physically demanding over time, and this leads to fatigue, to strain, to a constant awareness that even basic actions require energy and control. And all of this exists within a system that is limited in duration. Oxygen tanks contain only so much supply. CO2 scrubbers have finite capacity. Cooling systems rely on power and fluid circulation, meaning that a spacesuit can support life for hours, but not indefinitely. And this is the reality of survival in space. It is not about enduring the environment. It is about continuously maintaining a fragile balance within a system that must never fail, because the moment it does, the environment you are inside disappears and the environment outside takes over instantly. And this leads to an important realization that survival in space is not stable. It is temporary. It is conditional. It depends entirely on technology functioning perfectly at all times. And as we move forward, this dependence expands beyond individual suits into something even more complex. Entire spacecraft designed to sustain life over longer periods. And with that complexity comes new risks, new challenges, and new points of failure that must all be managed simultaneously. Inside a spacecraft, the situation feels different, more stable, more controlled. But the reality is that the margin for survival is still incredibly narrow, because the only thing separating you from the vacuum of space is a structure that must remain intact at all times. And that structure, despite its sophistication, is often much thinner than people imagine, typically only a few millimeters thick, designed to balance strength with weight, because every additional kilogram increases the cost and complexity of launching the spacecraft into orbit. And this creates a fundamental constraint. The walls must be strong enough to hold pressure, but light enough to be practical. And this balance means that while spacecraft are engineered with precision, they are not indestructible. They exist in an environment where even tiny objects can carry enormous energy. Because in orbit and in deep space, velocity is the key factor. Objects travel at tens of thousands of kilometers per hour. And at those speeds, even something as small as a grain of sand or a fragment of paint can impact with the force of a bullet. And when such an object strikes the hull, it can create damage, sometimes as minor, sometimes catastrophic. And this introduces a constant background risk that cannot be completely eliminated. Shielding systems such as multi-layered barriers can reduce the impact of small particles by breaking them apart and dispersing their energy. But there is always a limit. Something large enough or fast enough can penetrate. And if it does, the result is depressurization, the rapid loss of air from inside the spacecraft into the vacuum outside. And depending on the size of the breach, this can happen in seconds or minutes. But either way, the outcome is the same, if not contained. The internal environment collapses and the conditions necessary for survival disappear. And this is why spacecraft are designed with multiple layers of redundancy, compartments that can be sealed off, emergency procedures that can be activated, equipment that can be used to patch small leaks. But even with all of these measures, the underlying truth remains. The environment inside the spacecraft is artificial and fragile. It exists only as long as the systems maintaining it continue to function and the structure containing it remains intact. And beyond structural integrity, there are life support systems that must operate continuously. Oxygen must be generated or stored. Carbon dioxide must be removed. Water must be recycled. Temperature must be controlled. Waste must be managed. And all of these systems are interconnected. Failure in one can affect the others, creating cascading problems that must be addressed quickly. Because time is limited, there is no external source of air, no immediate resupply in deep space. Everything needed for survival must be carried with the spacecraft or generated within it. And this leads to another layer of complexity. Long-duration missions require systems that can operate reliably for months or years, with minimal maintenance and limited spare parts. And this is where engineering meets uncertainty, because no system is perfect. Components wear out, materials degrade, unexpected failures occur, and while redundancy can reduce risk, it cannot eliminate it entirely. And this creates a constant tension between stability and vulnerability, a recognition that survival depends not just on design, but on continuous operation, on monitoring, on maintenance, on the ability to respond to problems as they arise. And this is what makes living in space fundamentally different from living on Earth. On Earth, the environment supports you passively. In space, you must actively support yourself at all times. And the moment that support falters, the environment you are in reverts instantly to its natural state, vacuum. And with that comes the same sequence of events we have already explored: pressure loss, oxygen, deprivation, and the rapid breakdown of the human body. And as we continue this exploration, the focus begins to expand even further, because sustaining life in space is not only a technical challenge, but also a human one, involving not just systems and structures, but the minds and behaviors of the people who depend on them. Even if every system functions perfectly, even if pressure is stable, oxygen is flowing, temperature is controlled, and radiation is partially shielded, there is still another layer of survival that is far less visible, but equally critical: the human mind, because deep space does not only challenge the body, it places the mind into an environment it was never designed to handle. And this is where the nature of survival begins to shift from purely physical to something more subtle and more complex. Because for the first time in your life, you are no longer surrounded by a living world. There's no wind, no natural sound, no sense of open space in the way your brain understands it. Instead, you exist inside a confined artificial structure, fully aware that just beyond a thin wall, there's nothing that can support you, and that awareness does not disappear. It stays with you, quietly present in the background of every thought, every movement, every moment of stillness. And over time, that awareness can begin to reshape how you think and feel, because the human brain evolved in environments filled with sensory input, changing light, shifting temperatures, natural rhythms that guide sleep and alertness. And in space, those signals are either absent or artificially controlled. The day-night cycle is no longer defined by the rotation of Earth, but by the orbit of a spacecraft or by scheduled lighting systems. The horizon does not exist. The sense of up and down is replaced by weightlessness, and even your own body feels different as fluids redistribute and muscles are used in unfamiliar ways. And this constant subtle difference between expectation and reality requires continuous adaptation, not just physically, but cognitively, because your brain is always trying to interpret its environment, to predict what comes next. And in a place where the environment is so unlike anything it has evolved, to understand that process becomes more demanding, more effortful. And over long periods, this can lead to fatigue that is not purely physical, a kind of mental strain that builds gradually. And then there is isolation, not just being alone, but being separated from everything familiar, from the natural world, from immediate human contact beyond a small group, from the knowledge that help is close at hand. In deep space, communication itself becomes delayed. Messages take minutes or longer to travel. Conversations are no longer real time. And this changes the way people interact, the way problems are solved, the way support is given and received. And in this environment, small issues can feel larger. Conflicts can become more difficult to resolve. And maintaining emotional stability becomes as important as maintaining physical systems, because a breakdown in communication or cooperation can affect the entire mission. And this is why psychological preparation is a critical part of space travel. Astronauts are not only trained to operate equipment, but to work together under stress, to manage isolation, to maintain focus over long periods of time. And even with that preparation, challenges still arise, because no simulation on Earth can fully replicate the experience of being truly separated from it. And this introduces a question that goes beyond engineering. How long can the human mind remain stable in an environment that offers none of the natural cues it depends on? And while short missions have shown that adaptation is possible, the answer for longer journeys remains uncertain. Because as missions extend from months to years, the psychological demands increase. And unlike mechanical systems, the human mind cannot be repaired with spare parts. It requires rest, connection, meaning. And in deep space, those things must be created artificially, just like everything else. And this reinforces a deeper understanding of survival, that it is not just about keeping the body alive, but about sustaining the conditions that allow the mind to function. Because without that, even a perfectly engineered environment can become difficult to endure. And as we continue this exploration, the scale of the challenge begins to expand even further, moving beyond individual survival to the idea of sustaining human life over long distances and long periods, where both physical and psychological limits are pushed to their extremes. There is a point, as you move farther away from Earth, where distance stops being just a number and begins to fundamentally change the nature of survival itself. Because distance in space is not measured in miles in any meaningful way. It is measured in time, the time it takes for light to travel, the time it takes for signals to reach their destination, and the time it takes for any form of help to arrive. And as that distance increases, the relationship between you and Earth begins to shift. Because at first, communication is immediate. You speak and receive a response almost instantly. Guidance is available in real time. Support feels close. But as you move farther out, the changes at the distance of the Moon, there is already a delay of about 1 to 2 seconds, small but noticeable, enough to remind you that you are no longer in direct contact. At Mars, the delay grows to several minutes each way, meaning that a simple exchange of information can take 10 minutes or more And at greater distances, the delay becomes even longer, eventually reaching a point where communication is no longer a conversation, but a sequence of messages sent and received with long gaps in between. And this has profound implications for survival, because it means that decisions must be made independently. Problems must be solved without immediate assistance, and the crew must rely entirely on their own knowledge and resources. And this autonomy is both necessary and challenging, because it requires a level of self-sufficiency that goes beyond anything experienced in Earth-based environments. And at the same time, distance affects more than communication. It affects perception. Because as Earth recedes, it becomes smaller. First, a large presence in the sky, then a distant sphere, then eventually just a point of light. And this visual change can have a psychological impact, a shift in perspective that reinforces the reality of separation, of being truly away from home. And while some describe this as awe-inspiring, others experience it as a form of isolation, a reminder that the place that supports all known human life is now far away and inaccessible. And this leads to another layer of complexity, because in deep space, there is no possibility of rapid return. Missions are planned with trajectories that cannot simply be reversed at will. Fuel constraints, orbital mechanics, and timing windows all limit the ability to change course, meaning that once a mission begins, there is a level of commitment that cannot be undone easily. And this creates a situation where every decision carries greater weight. Every system must function, not just in the present, but for the entire duration of the journey. And this is where the concept of risk becomes different, because it is no longer about isolated events, but about cumulative exposure. The longer you are in deep space, the more you are affected by radiation. The more wear accumulates on systems, the more psychological strain builds. And all of these factors interact over time, shaping the overall viability of the mission. And this is why deep space travel is not simply an extension of orbital flight, but a fundamentally different challenge, one that requires rethinking how humans live, how they work, and how they sustain themselves over long periods in an environment that offers no support of its own. And as we move forward, this understanding leads to an even larger question, not just how we survive in space for short durations, but whether it is possible to live there long term, to establish a presence beyond Earth that is not temporary, but sustained. And exploring that question reveals just how far we still are from making that vision a reality. At this point, a deeper question begins to emerge, not just why you cannot survive direct exposure to deep space, but why even with all our technology, all our engineering, all our knowledge, we are still only visitors there, never truly residents, because if you look closely, everything we have built to keep humans alive beyond Earth is temporary, by design. Spacecraft, space stations, suits, they are not self-sustaining ecosystems. They are controlled environments that depend on constant maintenance, constant input, and constant stability. And this is where the fundamental limitation becomes clear. Life on Earth is supported by a planet-sized system, an atmosphere that recycles gases, oceans that regulate temperature, magnetic fields that deflect radiation, biological cycles that sustain food chains, and all of this operates continuously without direct human control. But in space, none of those systems exist naturally. They must be recreated artificially, and that recreation is never complete. It is always partial, always dependent, always fragile, because even the most advanced spacecraft cannot replicate the full complexity of Earth systems. Instead, they simplify, they reduce, they create just enough functionality to keep humans alive for a limited time. Oxygen is generated or stored, but not part of a global cycle. Water is recycled, but within closed constraints. Food is brought from Earth or produced in limited quantities. Waste is managed but not reintegrated into a natural system. And this means that every mission is constrained by resources, by how much can be carried, how efficiently it can be used, and how long the systems can operate before something runs out or fails. And this is why even on the International Space Station, in which orbits relatively close to Earth, resupply missions are essential, bringing food, water equipment, and replacement parts. Because without that continuous support, the station could not sustain life indefinitely. And as you move farther from Earth, this challenge becomes more severe, because resupply becomes less practical or impossible, meaning that everything needed for survival must be either carried at the beginning or generated along the way. And this leads to the concept of closed-loop life support, systems designed to recycle nearly everything: air-water waste, converting outputs back into inputs in a continuous cycle. And while progress has been made in this area, achieving near-perfect efficiency remains extremely difficult because small losses accumulate over time, materials degrade, systems become less effective, and maintaining the balance requires constant monitoring and adjustment. And this is where the difference between survival and sustainability becomes critical. Because surviving for days or weeks is one challenge. Sustaining life for years or generations is something entirely different. It requires not just functioning systems, but resilient systems capable of adapting to unexpected changes, capable of repairing themselves or being repaired with limited resources. And this is where current technology reaches its limits. Because while we can design systems that work under controlled conditions, predicting every possible failure over long durations is not possible. And so the question is not just whether we can survive in space, but whether we can create an environment that remains stable indefinitely without external support. And so far the answer is no. And this is why space remains a place we can explore, but not inhabit in the same way we inhabit Earth. Because the difference is not just distance or difficulty, it is the absence of a natural system that supports life. And until we can recreate that system in a fully self-sustaining way, human presence in space will remain temporary, dependent, and inherently vulnerable. And this realization begins to shift the perspective once again, because it highlights not only the challenges of space, but the uniqueness of the environment we come from. After understanding everything that deep space removes, everything your body depends on, and everything technology must replace, the perspective begins to change. Because what once felt ordinary now reveals itself as something remarkably precise. The environment of Earth is not just suitable for life, it is finely balanced in ways that are easy to overlook precisely because they are constant. The pressure at the surface is just right to keep water stable in liquid form to keep gases dissolved in your blood, to allow breathing to occur without effort. The composition of the atmosphere provides oxygen at a concentration that supports metabolism while diluting it enough to reduce fire risk. The magnetic field shields the surface from charged particles. The ozone layer absorbs harmful ultraviolet radiation, and the temperature range across most of the planet allows liquid water to exist, enabling the chemical processes that life depends on. And all of these factors work together continuously, forming a system that does not require active management from you. You do not regulate atmospheric pressure. You do not filter radiation. You do not balance oxygen levels. It all happens automatically. And this is what makes Earth fundamentally different from any environment we have discussed so far, because it is not just habitable, it is self-sustaining. It maintains its own balance through interconnected processes that operate across the entire planet. And this creates a level of stability that is difficult to replicate artificially, because any attempt to recreate these conditions in space must simplify them, reduce them to manageable systems, and in doing so, it loses the redundancy and resilience that come from scale. Earth systems are vast and interconnected. If one process fluctuates, others can compensate. But in a spacecraft or habitat, the margin for error is much smaller. A single failure can have immediate consequences, and this highlights a deeper truth about survival, that it is not just about having the right conditions at a single moment, but about maintaining those conditions over time in the face of change. And this is where Earth excels. It provides a stable baseline that supports life continuously. And when you compare that to the environment of deep space, the contrast becomes striking. Because space offers none of these stabilizing factors, it does not maintain pressure. It does not regulate temperature. It does not shield against radiation. It does not recycle resources. It simply exists, governed by physical laws that do not prioritize life. And this is why exposure to deep space is so immediately destructive, because it represents the absence of everything that makes Earth livable. And understanding this shifts the narrative from one of fear to one of perspective, because it reveals that the conditions you experience every day are not universal. They are specific, rare, and valuable. And this leads to a final layer of understanding, that while humanity may continue to explore space to extend its reach and its knowledge, the place where life exists naturally, where survival does not require constant technological support, remains here on this planet. And that realization carries implications not just for science or exploration, but for how we understand our place in the universe and the environment that makes our existence possible. There is a powerful idea that appears again and again in conversations about space. The idea that one day humanity will simply leave Earth behind, that we will expand outward if they settle new worlds and become a species no longer tied to a single planet. And while this vision is compelling, almost comforting in the way it suggests limitless possibility, it begins to change when you examine it through the lens of everything we have explored so far, because the question is no longer just whether we can reach other places, but whether we can truly live there without carrying Earth with us. And this is where the distinction becomes important. Because every plan for survival beyond Earth depends not on replacing Earth, but on recreating small controlled fragments of it, sealed habitats, pressurized structures, artificial atmospheres, systems that must constantly operate to maintain conditions that Earth provides freely. And this means that even as we move farther away physically, we remain dependent conceptually, dependent on the same environmental requirements, the same balance of pressure, oxygen temperature, and protection from radiation. And this dependence does not diminish with distance. It becomes more critical, because the farther we go, the less support we can receive, and the more self-contained our systems must be. And this leads to an important realization that leaving Earth does not mean escaping its influence. It means attempting to replicate it under far more difficult conditions. And that replication is not simple, because Earth is not a single system. It is a network of interacting processes that have evolved over billions of years. And when we attempt to recreate even a small part of that system, we are simplifying it, reducing it to manageable components. And in doing so, we remove layers of resilience that exist in the natural world. And this is why long-term survival in space remains such a challenge. Not because we lack the ability to build structures or generate oxygen, but because sustaining those systems over time without failure requires a level of reliability that is difficult to achieve. And this becomes even more complex when you consider the human element, because people are not static components. They require food, water, social interaction, psychological stability, and all of these needs must be met within the same constrained environment. And any imbalance can affect not just one individual, but the entire system. And so the vision of escaping Earth transforms into something more nuanced. Not a simple transition from one world to another, but an ongoing effort to maintain life within environments that are fundamentally hostile to it. And this does not make exploration impossible, but it reframes it, shifting the focus from expansion to sustainability, from reaching new places to understanding how to exist within them without losing the balance that life depends on. And as this understanding deepens, it begins to connect back to the original question, not just why no one can survive deep space, but why survival anywhere beyond Earth requires such careful control, because the absence of natural support means that every aspect of life must be actively maintained, and that maintenance never stops. As we continue to follow this path, another layer of understanding begins to take shape, one that is less about biology or engineering and more about the underlying rules that govern everything we have discussed. The laws of physics, because every challenge we have encountered, pressure loss, oxygen deprivation, temperature imbalance, radiation exposure, is not the result of a flaw in design or a lack of effort. It is the direct consequence of physical laws acting exactly as they are supposed to. And this is what makes deep space fundamentally different from other environments. Because it is not simply difficult, it is defined by conditions that do not support life as we know it. And this leads to an important distinction. Technology can solve many problems, but it does so within the boundaries set by physics. It can create pressure by containing gases, but it cannot eliminate the effects of vacuum outside that containment. It can generate oxygen, but it cannot remove the need for it. It can shield against radiation, but only to a certain extent, because high-energy particles can penetrate materials and interact in complex ways. And this means that every solution we develop is partial. It reduces risk but does not remove it entirely. And this is not a limitation of human capability. It is a reflection of the environment itself, because space is not designed for life. It does not adjust to accommodate it. It remains constant, governed by the same principles regardless of whether life is present or not. And this is where expectations must be aligned with reality, because it is easy to imagine that with enough advancement, any environment can be made habitable. But in practice, each step toward that goal reveals new layers of complexity, new interactions that must be managed, new constraints that must be considered. And this is particularly evident when we look at the idea of long-duration missions or permanent settlements, because maintaining stability over time requires not just initial solutions, but continuous adaptation. Systems must be able to respond to changes, to repair themselves or be repaired, to operate under varying conditions without failure. And achieving that level of robustness is extremely challenging, especially in an environment where external support is limited or non-existent. And so the limits of technology are not just about what we can build, but about how reliably those systems can function over extended periods under constant stress. And this brings us back to the core idea that survival in deep space is not prevented by a single obstacle, but by the combination of many factors, each one rooted in fundamental physics. And this combination creates an environment where life cannot exist naturally and where artificial support must continuously compensate for every missing condition. And this continuous compensation is what defines the boundary between survival and exposure, because the moment it stops, the environment reasserts itself immediately. And this is why the question of survival in deep space is ultimately not about endurance, but about control. Control of conditions, control of systems, control of interactions, and maintaining that control without interruption is the central challenge that defines human presence beyond Earth. Imagine, just for a moment, something that seems almost impossible, that you survived the first minute of exposure, that somehow pressure loss did not immediately destroy your internal balance, that oxygen deprivation was delayed, that your body remained functional just a little longer than physics normally allows. What would happen next is not relief, not adaptation, but the continuation of a deeper and more relentless breakdown. Because the processes we have described do not stop, they compound. And even if consciousness could be maintained beyond those first seconds, the environment would continue stripping away stability at every level. Your circulatory system would still be compromised. Gas bubbles would continue forming and expanding, disrupting blood flow and damaging tissues. Your cells would begin to lose their ability to regulate internal pressure and chemical balance. Membranes would weaken, signaling pathways would fail. And even as these microscopic changes unfold, larger systems would begin to collapse, because without stable pressure and oxygen delivery organs cannot function in coordination. The heart may still beat, but it is no longer supporting an organized system. The brain may still receive signals, but they are incomplete, distorted, fragmented, and this creates a state where the body is technically active, but no longer operating as a coherent whole. And at the same time, temperature imbalance would begin to assert itself more clearly. Heat would continue radiating away from the body, while external radiation from nearby stars could heat exposed surfaces, creating uneven thermal stress. And although this would not be the immediate cause of death, it would contribute to the overall instability, pushing the body further away from any state that resembles normal function. And beyond all of this, radiation exposure would continue, interacting with cells, damaging DNA, disrupting molecular structures. And while these effects would not manifest immediately in the way pressure loss does, they would accumulate, adding another layer of irreversible damage. And what becomes clear in this scenario is that survival in deep space is not limited by a single threshold that can be overcome. It is limited by a system of interdependent processes that all fail when environmental support is removed. Even if one process could be delayed, others would continue. And this creates a situation where extending survival by seconds or even minutes does not change the outcome. It only reveals more of the underlying mechanisms at work. And this is why discussions about survival often focus on the initial moments, because beyond that point, the trajectory is already determined. The body is no longer moving toward recovery, but toward increasing dysfunction. And this understanding reinforces the idea that deep space is not something the human body can gradually adapt to. It is an environment that requires complete separation from direct exposure. And without that separation, the outcome is not uncertain. It is inevitable. And this inevitability is not dramatic. It is simply the result of physical laws acting consistently. And as we continue this exploration, the focus begins to shift again, moving from the individual experience to the broader question of whether any environment beyond Earth can support life in a more stable way, and what it would take to create conditions where survival is not measured in seconds, but in years or generations. It is natural to think that if deep space itself is so hostile, then perhaps the solution lies on other worlds, planets or moons where conditions might be more stable, where there is at least some atmosphere, some surface, some structure to stand on. And while this idea is appealing, it becomes more complex when you examine the actual conditions that exist beyond Earth. Because most environments in our solar system do not remove the challenges of space. They simply rearrange them. On Mars, for example, there is an atmosphere, but it is less than 1% of the pressure found on Earth, far too thin to support human life, composed mostly of carbon dioxide, unbreathable without processing. And while the presence of an atmosphere reduces some aspects of vacuum exposure, it does not eliminate the fundamental problems. Pressure is still insufficient to prevent embolism without protection. Oxygen is absent, and radiation levels are significantly higher due to the lack of a strong magnetic field. And temperature on Mars fluctuates widely, often far below freezing, creating an environment that is not immediately lethal in the same way as open space, but still entirely incompatible with unprotected human life. And this pattern continues across other celestial bodies. The Moon has no atmosphere at all, essentially the same vacuum conditions as deep space, with extreme temperature swings between sunlight and shadow. The moons of Jupiter and Saturn may contain water in the form of ice or subsurface oceans, but they are far from the sun, extremely cold, and in some cases exposed to intense radiation from planetary magnetic fields, and even on bodies with thicker atmospheres, such as Venus. The conditions are not more forgiving, but more extreme. surface temperatures high enough to melt lead, pressures dozens of times greater than Earth's, and clouds composed of corrosive chemicals. And what this reveals is that there is no simple alternative to Earth within our immediate cosmic neighborhood, no place where human life can exist naturally without extensive modification of the environment or continuous technological support. And this leads to the concept of habitats, controlled environments built on or within these worlds, designed to recreate Earth-like conditions locally. But as we have already seen, creating such environments is not trivial. It requires maintaining pressure, providing breathable air, shielding against radiation, regulating temperature, and managing resources. And all of these systems must function reliably over long periods in environments that offer little to no natural support. And this brings us back to the same core principle, that survival beyond Earth is not about finding a place that is slightly better than space. It is about building systems that can compensate for what is missing. And those systems must operate continuously, because the underlying environment does not change. It remains hostile, governed by the same physical laws that make deep space so unforgiving. And this realization reframes the idea of exploration once again, because it shows that while other worlds may offer different challenges, they do not remove the need for protection. They simply change the form it takes. And as we move forward, this leads to an even broader perspective, one that extends beyond individual planets to the vast distances between stars, where the challenges become even more extreme and the concept of survival takes on an entirely different scale. At some point, the scale expands beyond planets, beyond missions within our solar system, and into something far more difficult to grasp, the space between stars, where distance is no longer measured in millions of miles, but in light years. And this is where the concept of deep space reaches its most extreme form, because interstellar space is not just empty, it is profoundly empty, with density so low that a single cubic centimeter may contain only a few atoms. And while that might sound like a detail without consequence, it defines the environment completely, because with so little matter present, there is nothing to provide pressure, nothing to carry heat, nothing to shield against radiation, just a vast, continuous vacuum extending in every direction. And in that environment, every challenge we have discussed does not disappear. It becomes more absolute, because there are no nearby planets to offer resources, no magnetic fields to provide partial protection, no atmospheres to absorb energy, only the background radiation of the universe and the steady stream of high-energy particles moving through it. And this creates a setting where survival is not just difficult, but fundamentally disconnected from anything familiar, because even the idea of orientation begins to change. There is no horizon, no reference point, only distant stars separated by immense distances. And this has implications not just for navigation, but for perception itself, because the human mind relies on spatial cues to understand its surroundings. And in an environment where those cues are minimal or absent, maintaining a sense of position and direction becomes more abstract, more dependent on instruments than intuition. And then there's the question of time, because traveling between stars with current technology would take tens of thousands of years, far beyond a human lifetime. And even with advanced theoretical propulsion systems, that could reach a fraction of the speed of light, the journey would still take decades. And during that time, every system required for survival would need to function continuously, without failure, without resupply, without the possibility of external assistance. And this introduces a level of complexity that goes beyond engineering, because it requires not just maintaining life, but sustaining it across generations, creating environments where people could live, work, and reproduce entirely within a spacecraft. And this concept, often referred to as a generational mission, brings with it a new set of challenges: biological, psychological, ethical, and technological, because the individuals who begin the journey would not be the same individuals who complete it, and the systems supporting them would need to operate reliably across timescales far longer than anything currently achieved. And this highlights the true scale of the challenge, because interstellar space is not just a larger version of deep space. It is an environment where the limitations of distance, time, and isolation all converge, creating conditions that push every aspect of survival to its limits. And as we consider this scale, it becomes clear that the question is no longer simply whether humans can survive deep space, but whether we can sustain life across distances and durations that fundamentally reshape what survival means. As the distance between stars becomes the focus, another constraint emerges, one that is deeply tied to the laws of physics and affects every attempt to move through space: energy. Because motion in space is not just about direction or speed. It is about the energy required to accelerate mass and then decelerate it again. And this is where the challenge of interstellar travel becomes particularly clear, because accelerating a spacecraft to even a small fraction of the speed of light requires enormous amounts of energy, far beyond what chemical rockets can provide. And while alternative propulsion concepts such as nuclear fusion, antimatter, or light sails have been proposed, each comes with its own limitations. Fusion requires conditions that are difficult to sustain in a controlled and compact form. Antimatter is extremely difficult to produce and store, and light sails require massive external energy sources and still face the problem of slowing down at the destination. And this leads to a fundamental trade-off, because the faster you want to travel, the more energy you need. And the more energy you carry, the more mass you add, which in turn requires even more energy to move, creating a cycle that quickly becomes impractical. And this relationship is not a matter of engineering preference. It is a direct consequence of the equations that govern motion and energy. And so any attempt to travel between stars must operate within these constraints, finding a balance between speed, mass, and energy that allows the journey to be completed within a reasonable time frame. And even if such a balance could be achieved, the challenges do not end there, because maintaining life during the journey introduces additional requirements: power for life support systems, shielding for radiation protection, resources for food and water. And all of these must be sustained for the entire duration of the mission, which could span decades or longer. And this is where the problem of time becomes intertwined with the problem of energy. Because the longer the journey, the more resources are needed. And the more resources are needed, the greater the mass. And the greater the mass, the more energy is required to move it. And this interconnected system of constraints defines the limits of what is currently possible. Because even if we can imagine solutions in isolation, combining them into a single functional system that can operate reliably over long periods remains a significant challenge. And this is why interstellar travel with humans is not simply a matter of building a faster engine. It is a matter of solving a complex network of problems that span physics, engineering, biology, and human behavior. And until those problems are addressed, the idea of traveling between stars remains more conceptual than practical. And this reinforces the broader theme that has been developing throughout this exploration. That deep space is not just an environment to be crossed. It is a set of conditions that must be continuously managed, and managing those conditions over vast distances and long durations requires solutions that extend far beyond what is currently available. And as we continue this journey of understanding, the focus begins to shift once more, moving from the technical challenges of reaching other stars to the deeper question of what it would mean to live in such environments, not just physically, but as a society, as a continuation of human experience beyond the boundaries of Earth. If traveling between stars is not just a journey, but a lifetime, then the spacecraft itself is no longer a vehicle. It becomes a world, a closed environment where every aspect of life must exist within finite boundaries. And this changes the question of survival entirely. Because now it is not about enduring space for a short period. It is about creating a system where life can continue indefinitely without external support. And this introduces challenges that extend beyond engineering into the structure of daily existence. Because within such a system, every resource must be accounted for. Air must be continuously recycled. Water must be purified and reused. Food must be produced or stored with extreme efficiency. And waste must be processed in ways that return it back into usable forms. And this creates a cycle where nothing can be lost because there is no outside environment to replenish it. And maintaining this cycle requires precision because even small inefficiencies can accumulate over time, gradually reducing the availability of essential resources. And this is where the concept of a closed ecosystem becomes central, an environment where biological and mechanical systems work together to sustain life, plants producing oxygen and food, systems recycling water and nutrients, and humans existing as part of that cycle rather than separate from it. But achieving a fully stable closed ecosystem is extraordinarily difficult because natural ecosystems on Earth are complex and dynamic, involving countless interactions between organisms and their environment. And when we attempt to recreate even a simplified version of that system, we encounter challenges, imbalances in nutrient cycles, fluctuations in oxygen and carbon dioxide levels, unexpected interactions between species. And these challenges become more significant over long durations, because the system must not only function, but remain stable over time. And stability in this context does not mean constant. It means resilient, capable of adapting to changes without collapsing. And this is difficult to achieve in a confined environment where diversity is limited and external inputs are minimal. And beyond the physical systems, there is the structure of life itself. Because within a spacecraft that functions as a world, the routines of daily existence must be redefined. Work, rest, social interaction, all occurring within the same limited space, And this can create a sense of repetition, of monotony, where the environment does not change in the way natural environments do, and maintaining motivation and engagement over long periods becomes a challenge. Not because the tasks are difficult, but because they are constant. And this is where design becomes important, creating spaces that support not just physical needs, but psychological well-being, providing variation, opportunities for privacy, ways to maintain a sense of connection and purpose. And all of this must be achieved within the constraints of mass and volume, because every additional feature adds weight and complexity. And this again highlights the balance that defines survival in space, between what is necessary and what is possible, between efficiency and livability. And this balance must be maintained continuously, because the system is not static. It is always in motion, always consuming resources, always generating outputs, always requiring adjustment. And this constant management is what allows life to persist in an environment that does not support it naturally. And as we continue to explore this idea, the focus begins to shift once more, from the structure of the environment to the experience of the people within it. Because sustaining life is not only about maintaining systems, but about maintaining meaning, connection, and identity over time. When a journey extends beyond a single lifetime, when it becomes something that spans decades or centuries, a new reality emerges, one where the people who live within the spacecraft are no longer travelers in the traditional sense, but inhabitants of a place that is itself in motion. And this introduces questions that are not just technical, but deeply human, because the individuals who begin the journey choose to leave. They understand the risks, the constraints, the purpose. But those who are born during the journey do not make that choice. They inherit it. And for them, the spacecraft is not a temporary environment. It is the only environment they have ever known. And this changes the nature of identity, because their sense of place is not tied to a planet or a landscape, but to a constructed environment, a system of corridors and rooms and controlled conditions. And while this environment can be designed to support life, it cannot fully replicate the diversity and variability of a natural world. And this raises questions about development, about how growing up in such an environment affects perception, learning, and well-being. Because human development is shaped by interaction with surroundings, by movement through space, by exposure to a wide range of stimuli. And in a confined environment, those experiences are limited. And while technology can simulate aspects of them, it is not the same as direct interaction. And this leads to considerations about education, about how knowledge is passed from one generation to the next, about how skills are maintained and adapted over time. Because the survival of the system depends on the ability of each generation to understand and manage it, to repair systems, to make decisions, to respond to challenges. And this creates a continuous cycle of learning and teaching that must be sustained without interruption. And beyond knowledge, there is the question of purpose. Because the original mission may have been defined by those who initiated the journey, but over time, that purpose must be maintained or reinterpreted by those who continue it. And this is not guaranteed, because values and perspectives can change, priorities can shift, and maintaining a shared sense of direction requires communication, cooperation, and trust across generations. And this introduces ethical considerations, because those born into the system have limited ability to choose their environment. Their path is defined by the conditions they inherit, and this raises questions about autonomy and responsibility, about how decisions made by one generation affect the lives of those that follow. And these questions do not have simple answers, because they involve balancing the goals of exploration and survival with the rights and experiences of individuals. And this highlights the complexity of extending human presence beyond Earth, because it is not just about reaching new places, but about creating systems that support life in a way that is sustainable and meaningful over time. And as we reflect on this idea, it becomes clear that the challenge of deep space is not only physical or technical, it is also social and philosophical, involving the structure of human life itself. And this brings us closer to a final understanding that surviving deep space is not simply a matter of overcoming environmental conditions, but of redefining what it means to live within them. From a distance, space feels like the ultimate expression of freedom, endless, open, without boundaries, a place where nothing restricts movement or possibility. But as you move closer to the reality of living within it, that idea begins to reverse, because the more infinite the environment becomes, the more confined human life must be in order to survive. And this creates a paradox that sits at the center of deep space exploration. The larger the universe, the smaller the space you must occupy within it, because outside your protective environment, there is no support, no gradual adaptation, only immediate incompatibility. And so, survival requires containment, controlled volumes of air, regulated systems, defined boundaries that separate you from the vastness beyond. And this means that in the most expansive environment imaginable, your existence is limited to a narrow enclosure, a habitat that must maintain conditions with precision. And this changes the meaning of freedom, because movement is no longer about going anywhere at any time. It is about staying within the boundaries that keep you alive. Every action is defined by the environment you carry with you. Every decision must consider the stability of that environment. And this does not remove the sense of exploration, but it reframes it, because exploration becomes something that happens through instruments, through observation, through carefully planned excursions rather than direct interaction. And this is where the contrast between perception and reality becomes most clear, because what appears open and limitless is in practice one of the most restrictive environments for human life. And this restriction is not imposed by design, but by necessity. It is the only way to exist within a space that does not support life naturally. And understanding this begins to shift the narrative from one of escape to one of adaptation, because it shows that the challenge of deep space is not just reaching it, but existing within it in a way that preserves the conditions required for life. And this preservation requires constant attention, constant maintenance, and constant awareness of the boundary between inside and outside, because that boundary is what defines survival, and without it, the environment beyond takes over instantly. And this leads to a deeper appreciation of the environments we take for granted, because on Earth, the boundaries between life and environment are not so sharply defined. They are integrated, continuous, and stable, while in space they are absolute and must be actively maintained at all times. As we move toward a broader understanding, one final realization begins to settle in. not as a dramatic conclusion, but as a quiet recognition of how the universe operates, because everything we have explored, the vacuum, the radiation, the temperature extremes, the absence of natural support systems, all of it exists not as a challenge to overcome, but as the default state of reality. And this is perhaps the most important shift in perspective, because it removes the idea that deep space is hostile in the sense of being opposed to life. Instead, it is indifferent. It follows physical laws that apply everywhere equally, regardless of whether those conditions support life or not. And this indifference is what makes survival so difficult, because there is no adjustment, no accommodation, no gradual easing into compatibility. The environment remains constant, and life must either conform to it or create conditions that allow it to exist within it. And this is fundamentally different from environments on Earth where life has evolved alongside changing conditions, where systems have adapted over time. In space, there is no such co-evolution for human life. The environment is what it is, and the only way to survive is to bring your own conditions with you, to construct a space within space where the rules are modified locally to support life. And this construction is never passive. It requires energy, resources, maintenance, and constant vigilance, because the surrounding environment does not assist in any way. And this leads to a clearer understanding of why no one can survive deep space without extraordinary protection. Not because it is uniquely dangerous compared to other environments, but because it lacks everything that makes life possible. And that absence is complete. It is not a gradient, not a spectrum, but a state where the fundamental requirements for life are simply not present. And this is why exposure leads to immediate and irreversible consequences, because there is nothing in the environment to counteract the processes that begin once those requirements are removed. And this realization, while grounded in physics, also carries a certain clarity, because it highlights the distinction between environments that support life and those that do not. And in doing so, it emphasizes the significance of the conditions that allow life to exist at all. And as we continue forward, this understanding leads naturally into a final reflection, not just on space itself, but on the place where these conditions come together in a way that supports human existence without constant intervention. There is a moment, after understanding everything we have explored, when your awareness shifts from the vastness of space back to something much closer, something so familiar that it usually goes unnoticed, the thin layer of atmosphere surrounding Earth, because what once felt like empty air now reveals itself as a boundary, a protective envelope that separates life from a universe that does not support it. And this boundary is not thick, not in any meaningful cosmic sense. It extends only a few dozen kilometers in a way that matters for human survival. And beyond it, the conditions change rapidly. Pressure drops, temperature becomes unstable, radiation increases, and within a relatively short distance, the environment transitions from supportive to hostile. And yet, within that thin layer, every process required for life is sustained. Oxygen is available at the right concentration. Pressure is sufficient to maintain liquid water and stable biological function. Radiation is filtered and deflected. Temperature is moderated through atmospheric circulation. And all of this occurs continuously without direct effort. And this is what makes the atmosphere not just a feature of Earth, but a system, one that interacts with the surface, the oceans, and the magnetic field to create conditions that remain stable over time. And this stability is what allows life to exist, not just moment to moment, but across generations, because it provides a consistent environment in which biological processes can operate reliably. And when you compare this to the environment of deep space, the contrast becomes clear, because in space, none of these stabilizing factors exist. There is no gradual buffer, no protective transition, only an immediate shift to conditions that remove every support system your body depends on. And this is why the boundary matters so much, because it is not just the physical separation. It is the difference between a place where life is sustained and a place where it cannot exist without artificial intervention. And this understanding brings a sense of scale back into focus, because while space is vast and expansive, the region that naturally supports human life is incredibly small by comparison. And that small region is where every breath, every heartbeat, every moment of awareness takes place. And recognizing this does not diminish the significance of space exploration, but it adds context. It shows that what we are exploring is not just distance, but difference. The difference between environments that sustain life and those that do not. And this difference is defined by the presence or absence of specific conditions. And maintaining those conditions is what allows life to continue. And as we move toward the final stages of this exploration, that realization begins to take on deeper meaning, not just scientifically, but in the way it shapes how we understand our place in the universe. As the perspective continues to widen, the realization becomes more profound, because the conditions that support life on Earth are not just uncommon. They are part of a delicate balance that may be rare on a cosmic scale. And this is not a statement of certainty, but of observation, because when we look at the environments we have studied within our own solar system and beyond, we see variation, extremes, atmospheres that are too thin or too thick, temperatures that are too high or too low, radiation levels that are too intense. And while there may be other places where life exists, the combination of factors that allow complex life to thrive appears to be specific and finely tuned. And this does not mean that Earth is unique in an absolute sense, but it does suggest that the conditions we experience are not the default state of the universe. They are the result of a particular set of circumstances, and understanding this adds another layer to the idea of survival, because it shows that survival is not just about the ability of organisms to adapt. It is also about the environment providing a stable framework within which that adaptation can occur. And without that framework, the limits of adaptation are quickly reached. And this is exactly what we see when we consider deep space. Because no matter how resilient the human body is within its natural range, it cannot function when the foundational conditions are removed entirely. And this reinforces the idea that life as we know it is closely tied to specific environmental parameters: pressure, temperature, chemical composition, radiation levels, all interacting in ways that support biological processes. And when any of these parameters move outside certain ranges, the system becomes unstable. And in deep space, all of them are outside those ranges simultaneously. And this is why survival there is not a matter of endurance, but of reconstruction, of building environments that restore those parameters artificially. And even then, the stability achieved is limited compared to the natural systems found on Earth. And this leads to a broader understanding of exploration, because it shows that the goal is not simply to move outward, but to understand the conditions that make life possible, to recognize where those conditions exist and how they can be sustained. And this understanding shapes the way we approach future missions, the way we design habitats, and the way we think about long-term human presence beyond our planet. And as we approach the conclusion of this journey, the focus begins to return once more to the individual, to the experience of being alive within these conditions, and to the realization that the environment supporting that experience is both specific and significant in ways that are easy to overlook until they are placed in contrast with everything that exists beyond it. After everything we have explored, there is one final layer that becomes impossible to ignore. Your body was never designed for space, not in any sense of the word. Every system within you, every cell, every chemical process has been shaped by a single environment over millions of years, Earth. And this shaping is not superficial. It is embedded at every level of your biology, from the way your lungs exchange gases to the way your blood carries oxygen, from the way your bones maintain density under gravity to the way your cells regulate pressure and fluid balance. All of it assumes a specific set of external conditions, and those assumptions are not flexible beyond a certain range because they are not conscious choices. They are the result of evolution, of countless generations adapting to a stable environment. And this is why when those conditions are removed, the body does not gradually adjust. It begins to fail, not because it is weak, but because it is specialized. It is optimized for a particular set of circumstances. And outside those circumstances, the mechanisms that normally sustain life no longer function as intended. And this becomes clear when you consider how many systems depend on external pressure, oxygen availability, temperature stability, and radiation protection. These are not optional features. They are foundational, and without them, the processes that keep you alive cannot operate. And this highlights an important distinction. Adaptation has limits. The human body can adjust to changes within a certain range, higher altitude, lower temperature, variations in gravity for short periods. But beyond those limits, the adjustments are no longer sufficient. And this is where deep space exists, far outside the range of conditions that human biology can tolerate. And this is why survival, that is not a matter of training or resilience. It is a matter of environment, because without recreating the conditions that your body expects, the outcome is determined by physics, not by willpower. And this understanding shifts the focus from the idea of conquering space to the idea of respecting the constraints it imposes, because those constraints are not arbitrary. They are defined by the interaction between biological systems and physical laws, and recognizing that interaction provides a clearer view of what is possible and what is not. And as we continue toward the conclusion of this journey, the clarity begins to settle into something more reflective, a recognition of the relationship between the body and the world it inhabits, and how closely those two are connected. When you step back and look at the universe without the filters of storytelling or expectation, what you see is not a place designed for life, but a system governed by consistent rules, rules that apply everywhere equally, from the smallest particles to the largest structures. And within that system, life exists, not because the universe is tailored to support it, but because certain conditions arise in specific locations that make it possible. And Earth is one of those locations, a place where the balance of forces and materials creates an environment where complex systems can develop and sustain themselves. But outside of those locations, the universe remains what it fundamentally is, a vast expanse where energy and matter interact according to physical laws without regard for biological needs. And this perspective does not diminish the significance of life. It places it within a broader context, showing that life is something that emerges under particular conditions rather than something that the universe inherently provides. And this is why deep space feels so different when understood at this level, because it represents the absence of those conditions, not as an anomaly, but as the baseline state. And this baseline is defined by vacuum, by radiation, by temperature extremes, by distances so large that interaction becomes rare, and within that baseline life cannot exist without intervention. And this intervention, the creation of artificial environments, is what allows humans to explore beyond their natural habitat. But it also highlights the limits of that exploration, because every step away from Earth requires additional layers of support, additional systems to maintain the conditions that life depends on. And each of those systems introduces complexity and potential points of failure. And this leads to a deeper understanding of what it means to survive in space. It is not about enduring the environment. It's about continuously maintaining a different environment within it. And that maintenance is what defines the boundary between life and non-existence in space. And as we move closer to the end of this exploration, that boundary becomes more than just a technical concept. It becomes a point of reflection, a way of understanding the relationship between life and the universe in which it exists, and how that relationship shapes the possibilities and limits of our presence beyond Earth. At some point, the idea quietly settles in that space could become a second home, not immediately, not easily, but eventually, through progress, through technology, through time. And this idea is not entirely unrealistic, but it carries a subtle illusion, because it assumes that space can be transformed into something like Earth, when in reality what we are doing is the opposite. We are bringing pieces of Earth into space, isolating them, maintaining them, protecting them against an environment that never changes to accommodate us. And this distinction matters because it defines the limits of what is possible. A home is not just a place where you can survive. It is a place where life is supported naturally, where the environment contributes to your well-being without constant intervention. And in space, that does not exist. Every habitable space must be constructed, every condition must be maintained, and this maintenance is continuous. It does not stop, it does not rest, and this is why even the most advanced concepts of space habitats are not independent ecosystems. In the same way Earth is, they are controlled systems operating within narrow margins, and those margins must be preserved at all times. This leads to a quiet realization that even if humanity expands beyond Earth, even if we establish habitats on other worlds or in orbit, those places will not replace Earth. They will depend on the same principles, the the same conditions, the same requirements, and this does not diminish their value, but it reframes their role. They are extensions of human presence, not replacements for the environment that made that presence possible in the first place. And this perspective changes the way we think about exploration because it shifts the focus from finding a new home to understanding how to sustain life within environments that do not provide one naturally. And this understanding becomes more important as we consider the long-term future because it highlights the difference between possibility and practicality, between what can be imagined and what can be maintained over time. And as this realization settles in, it begins to connect back to everything we have explored, the immediate effects of exposure, the dependence on systems, the limits of adaptation, all pointing toward the same conclusion. That space is not a place we can inhabit in the same way we inhabit Earth. It is a place we can visit, explore, and carefully exist within under specific conditions. And those conditions must always be preserved. Even under the best possible circumstances, with advanced technology, well-designed habitats, and carefully managed systems, survival in space remains temporary, not because it is impossible to extend it, but because it is always dependent on conditions that must be actively maintained. And this dependence introduces a time factor that cannot be ignored, because every system has a lifespan. Materials degrade, components wear out, resources are consumed. And while maintenance and repair can extend functionality, they cannot eliminate the need for eventual replacement or replenishment. And this creates a situation where long-term survival requires not just stability, but renewal, the ability to replace what is lost, to repair what is damaged, to adapt to changes that occur over time. And achieving this level of sustainability in space is extremely challenging because it requires systems that are not only efficient, but regenerative, capable of operating in cycles that can continue indefinitely. And while some progress has been made in this direction, the complexity of such systems remains high because they must integrate multiple processes: air recycling, water purification, food production, waste management, all working together without interruption. And any imbalance in one part of the system can affect the others, creating a cascade of effects that must be corrected. And this is where the concept of permanence becomes difficult to define, because even if a habitat can sustain life for years or decades, it is still operating within constraints that require ongoing effort to maintain. And this is fundamentally different from life on Earth, where the environment provides a baseline of stability that reduces the need for constant intervention. And this difference is what makes survival in space inherently temporary, because it is not supported by the environment itself. It is supported by systems that must remain functional at all times. And this leads to a broader understanding of what it means to exist beyond Earth. It is not a state of independence, but a state of managed dependence, where life continues as long as the conditions required for it are preserved. And when those conditions are no longer maintained, the environment returns to its natural state, and the same processes we have explored from the beginning take over once again. And as we move toward the final chapters, this understanding begins to take on a more reflective tone, not as a limitation, but as a perspective on the relationship between life and the environments that support it. At this point, everything begins to feel closer, more immediate, because the story is no longer about distant stars or extreme environments. It is about something happening right now, something so constant that it disappears into the background of your awareness, your breath, because every breath you take is a direct interaction with the environment that sustains you. Oxygen entering your lungs, carbon dioxide leaving, pressure guiding the movement of air, all of it occurring automatically, seamlessly, without effort. And yet each part of that process depends entirely on the conditions surrounding you. Remove those conditions, and the process stops instantly, not gradually, not with warning, but immediately. And this is what makes breathing more than just a biological function. It is a connection, a continuous exchange between your body and the world around you. And that exchange only works because the environment supports it, because the air has the right composition, because the pressure allows gases to move, because the temperature keeps the system stable. And when you consider deep space in contrast to this, the absence becomes clear. There is no medium for that exchange, no pressure to guide it, no reservoir of oxygen to draw from. And this absence is what makes survival impossible, not because the body forgets how to breathe, but because there is nothing to breathe, nothing to interact with. And this brings the entire concept of survival back to a simple but profound idea, that life is not just contained within the body. It exists in relationship with its environment, and that relationship must be maintained continuously. And this is why the environment matters so much, because it is not separate from life. It is part of it. And this realization shifts the perspective once again, because it shows that what feels internal is actually shared, that every breath, every heartbeat, every moment of awareness is supported by conditions that extend beyond the body itself. And recognizing this does not make space less fascinating, but it makes Earth more significant, because it highlights the role of the environment in sustaining life in a way that is easy to overlook when those conditions are stable and constant. There is a moment, somewhere in this journey of understanding, when space stops being an abstract concept and becomes something more defined, not just a backdrop for exploration, but an environment with specific properties that shape what is possible within it. And this moment is not dramatic. It does not arrive with sudden clarity. It builds gradually as each layer of explanation settles into place, until the idea of deep space becomes less about mystery and more about structure, vacuum pressure, radiation temperature, all interacting in ways that create a consistent and predictable environment. And once you see that structure, the question of survival becomes clearer, because it is no longer about uncertainty. It is about compatibility. Whether the conditions required for life exist within that environment, and in deep space they do not in any natural sense. And this understanding removes the need for speculation about what might happen, because the processes are already defined. We know how the body responds to pressure loss. We know how oxygen deprivation affects the brain. We know how radiation interacts with cells. And when all of these factors are combined, the outcome is not ambiguous. It is determined by the interaction between biology and physics. And this is what makes the conclusion feel less like a warning and more like a statement of fact, that without protection, deep space is not survivable, And this does not reduce the wonder of space. It refines it, because it allows us to appreciate both its beauty and its reality at the same time. The vastness, the distance, the complexity of the systems within it, and also the conditions that make it fundamentally different from the environment in which human life exists. And this dual perspective is what makes the study of space so compelling, because it reveals both the possibilities of exploration and the boundaries that define it. And as we move toward the final chapters, this understanding begins to settle into something quieter, more reflective, a sense of perspective that connects the vast scale of the universe with the immediate experience of being alive within a specific set of conditions, and how those two ideas coexist in a way that shapes our place within the cosmos. There is a boundary you cross every second of your life without ever thinking about it. Not a visible line, not something you can point to, but a constant interface between you and everything around you. And that boundary is what keeps you alive, because it separates the conditions your body needs from the conditions that would immediately destroy it. And on Earth, that boundary feels invisible, because the environment on both sides of it is compatible. The air you breathe, the pressure on your skin, the temperature around you, all exist within the range your body expects. And so the boundary becomes seamless, almost non-existent in your awareness. But in space, that boundary becomes absolute, because beyond it, there is nothing that supports life. And this changes the way you understand it, because it is no longer just a passive separation. It is an active barrier that must be maintained at all times. And this barrier can take many forms: the hull of a spacecraft, the fabric of a spacesuit, the walls of a habitat. But in every case, its function is the same: to preserve the conditions inside against the environment outside. And what makes this boundary so critical is not just its presence, but its integrity, because it must remain intact without interruption. Even a small failure can allow the external environment to begin interacting with the internal one, and that interaction follows the same principles we have explored from the beginning. Pressure equalizes, gases move, energy transfers, and the conditions that support life begin to break down. And this is why so much of space engineering is focused on containment, on ensuring that this boundary remains stable, because it is the difference between a controlled environment and an uncontrolled one. And understanding this boundary brings the entire concept of survival into focus, because it shows that life in space is not about resisting the environment. It is about isolating yourself from it, creating a space within space where different rules apply, and maintaining that space with precision. And as this idea settles in, it becomes clear that the boundary is not just physical, it is conceptual. It represents the separation between environments that support life and those that do not, and recognizing that separation changes the way you think about both, because it highlights how much of what you experience depends on the conditions that exist just beyond your awareness. It is tempting to think that somewhere out there, beyond the environments we have examined, there might be regions of space that are more forgiving, places where conditions align in a way that makes survival easier. But as we look deeper into the structure of the universe, the pattern remains consistent, because the same physical laws apply everywhere, and those laws do not soften with distance. They do not become more accommodating, as you move farther from Earth, they remain constant, shaping environments according to the same principles regardless of location. And this means that the challenges we have explored are not unique to a specific region. They are inherent to the nature of space itself. Vacuum remains vacuum. Radiation continues to travel through space. Temperature differences persist wherever there is an imbalance of energy. And this consistency is what allows us to understand space scientifically. But it also defines its limits for human life, because it means that there is no hidden refuge where the rules change, no gradual transition to a more hospitable environment, only variations in intensity and composition. And this leads to a deeper understanding of why survival in deep space is not a matter of finding the right place, but of creating the right conditions, because those conditions do not exist naturally in the vast majority of the universe. And this realization brings a sense of clarity, because it removes the idea that survival might be possible if only we go far enough or look in the right direction. Instead, it shows that survival depends on the same factors everywhere: pressure, oxygen, temperature stability, radiation protection. And without those factors, life as we know it cannot exist. And this consistency is not limiting in a negative sense. It is informative. It provides a framework for understanding what is required to sustain life and where those requirements can be met. And as we approach the final chapters, this framework becomes the foundation for a broader reflection, one that connects the scientific explanation of space with the experience of living within a specific environment, and how that experience shapes our understanding of the universe as a whole. When people describe deep space as hostile, it often sounds emotional, almost dramatic, as if the universe itself is acting against life. But by now, the meaning of that word begins to change, because hostility in this context is not intention, it is incompatibility. It is the simple fact that the conditions required for human survival are absent. And everything we have explored leads back to this idea that space does not oppose life, it simply does not support it. And that distinction matters because it shifts the focus away from fear and toward understanding. Because once you recognize that the environment is neutral, governed by consistent laws, the question of survival becomes one of alignment, whether the requirements of the body match the conditions of the environment. And in deep space, they do not even partially, not even briefly, without protection. And this is why the effects we have described unfold so quickly, because there is no buffer, no intermediate state where the body can adjust. The transition from a supportive environment to a non-supportive one is immediate, and the body responds according to the same physical and biological principles that keep it alive under normal conditions. But now, those principles lead in a different direction, toward imbalance and failure rather than stability. And this is what makes deep space feel so extreme, not because it is actively destructive, but because it removes every factor that prevents destruction. And this understanding reframes the entire narrative, because it shows that survival is not about resisting an external force. It is about maintaining an internal environment that remains compatible with life. And when that environment is removed, the outcome is not unpredictable. It is defined. And this definition is what gives the concept of hostility its true meaning, Not danger in the sense of unpredictability, but certainty in the sense of outcome. And as this idea settles in, it begins to connect back to the earlier chapters, to the role of pressure, oxygen, temperature, radiation, all working together to create conditions that either support life or do not. And in deep space, all of those conditions fall outside the range that human biology can tolerate. And this is why survival. There's not a question of endurance or strength. It is a question of environment. And as we move closer to the conclusion, this perspective begins to shift once more from the nature of space to the significance of the environment that makes life possible. After exploring the extremes of deep space, the focus naturally returns to something much simpler, much closer, the environment you are in right now. And what becomes clear is that the conditions supporting your life are not dramatic. They do not demand attention. They operate quietly in the background. And because of that, they are easy to overlook. But when placed in contrast with the absence of those conditions in space, their significance becomes unmistakable, because every aspect of your environment contributes to your ability to exist without effort. The air provides oxygen at the right concentration. The pressure maintains the balance of gases in your body. The temperature allows your cells to function within stable ranges. The magnetic field and atmosphere reduce radiation exposure to levels that your body can manage. And all of these factors work together continuously, forming a system that supports life without requiring constant intervention from you. And this is what makes Earth fundamentally different from any environment we have examined, because it does not require you to create the conditions you need. It provides them. And this provision is what allows life to develop complexity, to grow, to evolve, because it removes the need to constantly maintain the basics of survival. And when you consider this in the context of deep space, the contrast becomes more than scientific. It becomes experiential, because it highlights the difference between living within a system that supports you and existing within one that does not. And this difference is not always visible, but it is always present, shaping every moment of your experience, and recognizing it does not change the environment itself, but it changes your awareness of it. It brings attention to the conditions that are normally taken for granted, and in doing so, it adds a layer of meaning to the concept of survival, because it shows that survival is not just about overcoming challenges. It is about existing within a set of conditions that make life possible in the first place. And as we approach the final chapter, this awareness begins to settle into a broader perspective, one that connects the scientific explanation of deep space with the personal experience of being alive within a specific environment, and how those two ideas come together to shape our understanding of the universe. When everything is stripped back to its simplest form, beyond stories, beyond expectations, beyond the images we carry in our minds, what remains is a quiet understanding of the universe as it actually is. Not a place built for life, not a place that adapts to us, but a vast system where matter and energy follow consistent laws without exception. And within that system, life appears only where conditions allow it. Not because the universe provides for it, but because in certain rare configurations, those conditions happen to exist. And this is what deep space represents. Not danger in the emotional sense, but the absence of those configurations, a place where the rules remain the same, but the outcomes are different because the parameters required for life are simply not present. And this understanding removes the illusion that space is waiting to be conquered or tamed. Instead, it reveals that what we call survival is the result of alignment, the alignment between biological systems and environmental conditions. And when that alignment exists, life continues. When it does not, life cannot persist. And this principle applies everywhere, from the smallest scale of cells to the largest scale of planets. And it is what defines the boundary between where life can exist naturally and where it cannot. And recognizing this does not make space less remarkable. It makes it more precise, more understandable, because it shows that the same laws that allow stars to form and galaxies to evolve also define the limits of life. And within those limits, humanity finds itself in a very specific position, on a planet where the alignment is stable, where the conditions are sustained, and where the processes that support life operate continuously without interruption. And as this realization settles in, it becomes less about the extremes of space and more about the clarity of understanding, a sense that what once seemed mysterious is now defined, not in a way that removes wonder, but in a way that deepens it, because it reveals the structure behind the experience and how that structure shapes everything that follows. And so the question that began this journey comes back into focus, not as something unanswered, but as something fully revealed. The real reason no one can survive deep space is not a single factor, not a single moment, not a single failure. It is the complete absence of every condition that life depends on, occurring all at once, without transition, without delay. Pressure disappears, gases come out of solution, fluids begin to vaporize, oxygen supply is cut off, the brain loses function within seconds, radiation continues to pass through the body, temperature becomes unregulated, and all of these processes are not separate. They are simultaneous, interacting with each other, reinforcing the overall outcome. And this is why survival is not possible, because there is no pathway for the body to adapt to all of these changes at once. No sequence in which one system can compensate for another. The environment does not allow for it. And this is what makes deep space fundamentally different from other extreme conditions. It is not a challenge that can be met with preparation alone. It is a condition that requires complete isolation from direct exposure. And this is why every human presence in space depends on technology, on systems that recreate a small part of Earth's environment within a controlled boundary and maintain it continuously. Because without that boundary, the environment outside takes over immediately. And this explanation, while grounded in physics and biology, carries a certain simplicity, because it shows that survival is not about overcoming the universe. It is about existing within the conditions that make life possible. And when those conditions are removed, the outcome follows naturally from the laws that govern everything else. And this is the reason. Not dramatic, not mysterious, but precise, consistent, and unavoidable. And understanding it brings the entire exploration to a point of clarity, where the question is no longer why survival is impossible, but how remarkable it is that it exists at all under the conditions we experience every day. After everything has been explained, after each layer of physics and biology has been carefully unfolded, What remains is not just information, but a shift in how you see things, a quiet adjustment in perspective that lingers even after the details begin to fade. Because understanding deep space is not only about knowing what happens out there, it is about recognizing what is happening here, in this moment, in this environment that supports you without effort. And that realization does not arrive suddenly. It settles in gradually as your awareness returns from the vast scale of the universe to the immediate experience of being alive, and you begin to notice the small things again. The feeling of air moving in and out of your lungs, the steady rhythm of your heartbeat, the stability of the ground beneath you, all of it supported by conditions that are so consistent they become invisible. And yet, those conditions are the reason you are able to experience anything at all. And this connection between understanding and awareness is what gives this exploration its depth, because it moves beyond explanation into perception, showing that the environment is not separate from your experience, it is part of it. And when you see that clearly, the idea of space changes, not because it becomes less interesting, but because it becomes more defined, more real, a place that exists according to its own rules. And those rules do not align with the needs of human life. And this alignment, or lack of it, is what shapes the boundary between where you can exist naturally and where you cannot. And recognizing that boundary does not create distance, it creates clarity, a sense of where you are within the larger structure of the universe and how the conditions around you make that position possible. And as the understanding settles, something else begins to happen, something softer, less analytical, more reflective, because the focus shifts away from explanation and toward experience. The rhythm of the words slows. The ideas become less about information and more about presence. And in that space, the contrast between deep space and your current environment becomes something you can feel rather than just understand, a sense of being held within conditions that support you, that allow your body to rest, your mind to slow, your awareness to soften. And this is where the journey gently changes direction, moving away from the intensity of explanation into a quieter space, where the details no longer need to be examined, only felt. And in this stillness, the vastness of space becomes less overwhelming, less distant, and more like a backdrop, something that exists beyond the boundaries of your immediate experience. While here, within those boundaries, everything is stable, everything is continuous, everything is enough. And this is not a conclusion in the traditional sense. It is a transition, a movement from understanding into rest, where the mind no longer needs to follow every detail, where the body can relax into the environment that supports it, and the awareness that has expanded outward can gently return inward, settling into a sense of calm that's grounded in the recognition of where you are and what allows you to be here. And as that calm deepens, the distinction between space and earth becomes less about contrast and more about appreciation, a quiet acknowledgement of the conditions that make this moment possible, and how those conditions continue without interruption, allowing you to rest, to breathe, to simply exist within them. At this point, there is nothing left to analyze, nothing left to break apart or explain, because everything that needed to be understood has already unfolded, And what remains is something quieter, something that does not require effort, a simple awareness that settles in the background of your thoughts. Because the universe has not changed, the laws that govern it remain the same. Deep space is still vast, still silent, still governed by pressure, radiation, and absence. And yet your relationship to it has shifted. It is no longer something distant and abstract. It is something defined, something understood. And in that understanding, there is no tension, no urgency, just clarity. And as that clarity settles, your attention naturally begins to soften, moving away from the edges of thought and into something more fluid, more relaxed. Because you no longer need to hold on to every detail. You can let them pass one by one, like distant points of light fading into the background. And as they fade, what remains is the simple experience of being here, within an environment that supports you without effort, where every breath continues without interruption, where every system in your body operates within the conditions it was made for. And this contrast between what exists out there and what exists here becomes less about difference and more about presence, because it brings your awareness back to the moment you are in, to the stability that surrounds you, to the quiet continuity of the systems that keep you alive. And in that continuity, there is nothing you need to do, nothing you need to change, just a gentle recognition that everything is already in place, already working, already supporting you in ways that do not require your attention. And as that recognition deepens, the mind begins to slow even further, thoughts becoming softer, less defined, drifting rather than focusing. And this is where the journey naturally begins to come to rest, not with a conclusion, but with a gradual fading, a movement away from structure and into stillness, where the boundaries between ideas begin to dissolve and the experience becomes less about understanding and more about simply being. And so you return not from a place you physically traveled to, but from an understanding that expanded outward and then gently came back, carrying with it a quiet sense of perspective, because the stars above you are still there, distant, unchanged, existing in the same vast space that does not support life. And yet here, beneath a living sky, everything is different, because this place, this thin layer of atmosphere, this balance of conditions, continues to hold you within it, to support every breath, every moment of awareness, every sensation of rest. And as you settle into that awareness, there's nothing you need to hold on to, nothing you need to remember in detail, only the feeling of being supported, of existing within a system that works without effort. And this feeling does not demand attention. It simply remains steady and quiet, like the rhythm of your breathing, like the gentle continuity of your heartbeat. And as you allow yourself to rest within that continuity, the contrast between space and earth becomes something distant, something that no longer needs to be examined. Because what matters now is the moment you are in, the stillness that surrounds you, the calm that slowly deepens as your thoughts drift further apart. And in that calm, the vastness of the universe does not feel overwhelming. It feels distant, almost comforting in its quiet consistency, while here everything remains close, stable, and present. And as that sense of presence becomes softer, more subtle, your awareness begins to fade into rest, not suddenly, not completely, but gradually, like a light dimming in a room that is already quiet. And in that quiet, there is nothing left to do, nowhere else to go. Only the gentle continuation of this moment, supported by the same conditions that have always been there, steady, reliable, and enough. And as you drift further into that stillness, the journey ends, not with an answer, but with a feeling, a calm understanding that settles into the background and stays with you quietly as you rest beneath a sky that has always been alive. As your thoughts begin to slow and the weight of everything we explored gently fades into the background, there's nothing left to analyze now, nothing left to figure out, only a quiet understanding that stays with you somewhere just beneath the surface of your awareness. Out there, beyond this world, the universe continues exactly as it always has, silent, vast, and indifferent, governed by laws that never change, never pause, never adjust for anything. And yet here, in this moment, everything is different, because you are still within the one place where those laws align just enough to allow you to exist without effort, to breathe without thinking, to rest without resistance. The air around you is still there, gently pressing, quietly supporting. Your body is still balanced, still stable, still held within conditions it understands. And maybe you don't need to think about it any further than that. Just notice it, softly, the way your breath moves, slow, steady, effortless, the way your body feels, supported, without needing to do anything at all. There's nothing to hold on to now. No need to follow every idea. No need to stay focused. You can let your thoughts drift. Let them become lighter, quieter, more distant, like stars, slowly fading into the night sky. And as they fade, what remains is simple. You are here. You are safe. You are supported. And everything around you is already working exactly as it should. So you can rest now. Let the universe stay out there, vast, distant, untouched, and let yourself settle here, in the quiet, in the stillness, in the gentle rhythm of your breath. Good night, and rest well, beneath the only sky you've ever needed